Welcome back to The Deep Dive. We're the show that digs deep into complex topics to pull out the critical knowledge you really need.
And today, we are definitely deep diving into something crucial, reactive chemical hazards. We're focusing on pure risk assessment, really.
Yeah, this is about self-preservation through knowledge. Our main source, it's a cornerstone text, Bretherick's Handbook of Reactive Chemical Hazards.
Right, it's this monumental compilation just cracking decades and decades of incidents reported in scientific and technical literature. A huge undertaking.
It's not just a book. It feels more like a global logbook of things going wrong chemically. So our mission today is pretty straightforward. We want to pull out the core principles, get a handle on the physics behind why things explode or react violently, and look at some, frankly, terrifying examples.
All to make sure you're properly informed about these inherent dangers. Knowledge is protection here.
Absolutely. So where did this massive effort even begin? What was the spark?
Well, the origin story is actually tied to a specific failure, a failure of information getting to the right people. The catalyst for Bretherick's work was this lab explosion back in 1964.
Okay, what happened?
It involved a pretty common mix, actually, chromium trioxide and acetic anhydride. Standard stuff in some labs.
Right. But here's the kicker, the thing that really pushed Leslie Bretherick, the compiler, into action.
Exactly. He discovered that the exact same combination had been publicly flagged as extremely hazardous 16 years earlier.
16 years, back in 1948.
Yes, 1948. The information was there, documented in some obscure journal article, but this was pre-internet, pre-databases.
So it was basically lost knowledge, buried somewhere.
Pretty much. A scientist, completely unaware of this history, just repeated the same hazardous procedure. And Bretherick realized the problem wasn't necessarily new dangers, but making existing knowledge accessible.
Wow. So people were literally rediscovering dangers the hard way.
That's what it looked like. His initial quick search turned up something like 300 similar incidents right away. That really launched his life's work, trying to make sure these unfortunate incidents, as he called them, wouldn't keep happening just because the info wasn't readily available.
Okay, so before we dive into the specifics, let's just establish the stakes here. Why does this compilation matter so much? We're not just talking about broken beakers, are we?
Oh, not at all. This scales up massively. We're talking potential for industrial disaster, civilian casualties, the works.
The handbook itself kind of grounds you immediately, right? It mentions a couple of really big ones in the introduction.
It does. It brings up two defining events. First, the Oppo explosion in Germany, 1921.
Oppo, that was ammonium nitrate, wasn't it?
Ammonium sulfate and ammonium nitrate mixture, yeah. About 4,500 tons of it detonated. It's still one of the largest non-nuclear man-made explosions ever recorded. Just shows the raw power stored in seemingly stable oxidizing salts when things go wrong on a massive scale.
Chilling. And the second example is maybe even more insidious because it wasn't a big bang. Bhopal.
Bhopal, India, 1984. Not an explosion in the traditional sense, but a massive release of highly toxic methyl isocyanate gas.
The consequences were just devastating, immediate deaths, and something like over 100,000 people left with permanent injuries.
That's right. It highlights the other side of reactive hazards. It's not always about explosive force. Sometimes it's about an unforeseen reaction generating enormous amounts of deadly material.
So these two examples together really frame the problem. It's about sudden, violent energy release, and it's about the unexpected creation of poisons.
Exactly. Which brings us back to the core message. You absolutely have to gather as much detailed information as possible before you start any chemical process you're not familiar with, or even when storing things you are familiar with, potentially.
Okay, let's get down to the nitty-gritty then, the fundamental physics. Why do some chemical reactions release energy, and when does that become a hazard?
Right. So all chemical reactions involve energy changes. You've got two main parts, activation energy and reaction energy.
Activation energy is like the push needed to get the reaction started.
Precisely. It's the energy barrier you have to overcome to break the initial chemical bonds. Once you're over that hump, the reaction energy takes over. And that determines if the process gives off energy or sucks it in.
Which leads us to the two big categories, exothermic and endothermic. Exothermic seems like the obvious danger zone.
It often is. Exothermic reactions release energy usually as heat, but sometimes light or sound too. And the danger is that released heat can speed up the reaction itself.
Creating a feedback loop. More heat, faster reaction, even more heat.
Exactly, a runaway reaction. That's a classic hazard scenario. But we absolutely cannot ignore the flip side, endothermic reactions.
Right, those are the ones that absorb energy. How are they hazardous? It seems counterintuitive.
Because they absorb energy into the structure of the product molecules themselves. Think of it like compressing a spring.
Ah, okay. So if a reaction takes in, say, 50 kilojoules to make a new compound, that energy isn't gone. It's now stored in that compound's bonds.
Precisely. It's intrinsic energy, or you could call it chemical strain, locked within the molecule. This makes the product itself inherently unstable. It's primed to release that stored energy later, maybe through decomposition, maybe with just a little nudge.
So the hazard definition covers both scenarios then?
Yes. A reactive hazard happens when energy is released either from an exothermic reaction going too fast or from an unstable endothermic compound decomposing, and the rate or sheer quantity of that energy is just too much for the surroundings to handle.
The flask, the reactor, the pipes, they just can't absorb or vent the heat or pressure quickly enough.
That's it, and that's when you get material failure, explosions, containment breaches, damage.
Let's get specific with the terminology then, especially around explosions. People throw terms around, but deflagration and detonation are very different beasts, right?
Hugely different, yes. Deflagration is, relatively speaking, the slower one. The reaction front, the zone where the chemistry is happening, moves slower than the speed of sound through the material.
Subsonic. So you still get pressure, obviously.
Oh, definitely. You get a rapid expansion of hot gases, creating significant pressure. Think of it like a powerful push outwards. This can knock down walls, like in the Flixborough vapor cloud incident back in '74. That was largely a deflagration event, but still incredibly destructive due to the scale and the pressure wave.
Okay, so deflagration is a big push. Detonation, though. That sounds more violent.
It is. Detonation is the extreme end. Here, the reaction front becomes supersonic. It travels faster than the speed of sound within the gas, liquid, or even solid material itself.
Faster than sound in the material. Wow.
And this isn't just expanding gas causing pressure anymore. It's a shock wave, a physical shock wave, propagating through the substance.
And that shock wave is the key difference.
It's absolutely critical. In a detonation, temperatures and pressures can be orders of magnitude higher than in a deflagration. The energy release is incredibly fast. We're talking microseconds. And that supersonic shock wave delivers immense force. It doesn't just push, it shatters. That's the fragmentation damage you associate with high explosives.
Right, shattering versus pushing, big difference. And we should also quickly mention dust explosions, shouldn't we? They fit in here too.
Definitely. Dust explosions are often overlooked when we focus on liquids and gases. Chemically, they might seem simpler, often just fine particles of a combustible solid reacting very quickly with air.
Like flour in a mill or coal dust.
Exactly. But the physics are brutal. The huge surface area of the fine particles means the reaction is incredibly fast, generating enormous volumes of hot gas almost instantly. This creates massive pressure effects that can easily destroy large structures like silos or factory buildings.
Okay, so understanding these mechanisms is key. Now, let's go back to the handbook itself. If you actually pick up this massive book, it's clear a lot of thought went into just organizing the information to prevent that original problem Bretherick identified.
Absolutely. The architecture is meticulous. First, the scope is vastest. Basically, any reactivity hazard reported for elements or compounds, alone or mixed, up to the end of 2004 in the later editions. But the real linchpin is the commitment to naming things correctly. Nomenclature.
Why is precise naming so critical in this field? Seems obvious, but what's the specific danger of getting it wrong?
Well, think back to that 1964 accident. Confusion over names or using old ambiguous terms can lead directly to disaster. Bretherick prioritized using unambiguous IUPAC names. That's the international standard, ensuring everyone, everywhere, is talking about the exact same molecule.
But people still use common names, right? Like acetone instead of propanone.
Of course. And the handbook accounts for that. It includes those common or trivial names like acetone or even trade names like oleum, but they're listed as synonyms, usually in parentheses. Critically, they cross-reference you to the main entry under the proper IUPAC name. So even if you search using an older term, you end up in the right place.
That's smart. It ensures consistency, and that structure must be even more important when you're dealing with reactions involving multiple chemicals, where the danger isn't the starting stuff, but something they create.
Exactly. That's where the cross-referencing system really proves its worth. If there's a known unstable intermediate or product that's the real source of the hazard, let's say the explosive, the nitrogen triide ammonia complex that forms when you mix ammonia and iodine.
Okay.
Now the entries for the starting materials, ammonia and iodine, which are stable on their own, will both point you directly to the main entry for that unstable nitrogen triiodide complex. It connects the cause, mixing A and B, to the effect unstable product C exploding.
It traces the actual hazard, but what if it's messy? Like you mix 3 or 4 things and they just go boom, and nobody's quite sure what unstable thing formed or if it was just the mix itself.
Yeah, that happens. And that's where the methodology becomes, let's say, pragmatic. If no specific unstable product can be clearly identified, the compiler had to make a choice. They select one of the reactants as the primary entry point for the incident report.
Arbitrarily.
Sometimes, seemingly so, yes.
Yeah.
The other reactants are then listed under that primary entry. Bretherick noted that often in these complex multi-reactant blowups, the reactant chosen as the primary entry was simply the most obvious oxidizing agent present. It's a practical way to make sure the incident gets recorded and linked to something, even if the detailed mechanism is murky.
Okay, that makes sense. Record the danger, even if the why is complex. Now, before we get into specific dangerous chemicals, there's the question of toxicity versus reactivity. Bretherick's focuses on reactivity, explosions, fires, but toxicity does creep in sometimes.
It does, but under a very specific condition. Toxicity is generally not the focus. The Handbook flags a toxicity hazard only when a chemical reaction produces a volatile poison in a way that a chemist might not reasonably foresee.
So if mixing 2 seemingly harmless things suddenly generates, I don't know, phosgene gas or something equally nasty out of the blue?
Exactly. If it's an unexpected toxic gas generation pathway, it gets mentioned because that's a hidden hazard related to the reaction itself.
But here's the really telling part, the insight that shows the limits. The book explicitly states it doesn't include warnings for generating hydrogen sulfide when you mix sulfides and acids.
Correct, and that omission speaks volumes. It underscores that this handbook, despite being incredibly comprehensive, is not Chem 101. It assumes a baseline level of chemical knowledge.
It assumes, basic, well-established hazards like H2S generation.
Precisely. It assumes you know that mixing sulfides with acid releases hydrogen sulfide, a notoriously toxic gas. That's considered fundamental training. The book reserves its warnings for the more obscure, the unexpected, the highly energetic pathways that lead to explosions or fires or these unforeseen toxic releases. It can't cover everything.
Right. It's a tool for experts assuming other knowledge. Okay, let's dive into the rogues gallery. Based on the sheer number of incidents reported in Bretherick's, what are the repeat offenders? Which oxidants show up again and again?
Yeah, looking at frequency is revealing. The top 5, based on the number of incidents linked to them, are probably perchloric acid, nitric acid, hydrogen peroxide, elemental chlorine, and sulfuric acid.
Wow, those are workhorse chemicals found everywhere.
They are, which partly explains their frequency. They're just used a lot.
Yeah.
But fundamentally, they are incredibly powerful oxidizing agents, capable of reacting violently with many other substances, especially organic materials or reducing agents.
Let's focus on perchloric acid for a moment. It seems particularly nasty because it has sort of a dual personality, right?
It does. Dilute perchloric acid is mostly just a strong acid, but concentrated perchloric acid, especially when heated, that's a different beast entirely. It becomes an extremely potent oxidizing agent and a powerful dehydrating agent.
And that combination is dangerous.
Extremely. It's notorious for reacting explosively with organic materials. This can happen by dehydrating them or by forming unstable organic perchlorate salts or esters, which can then detonate with heat or even just friction.
I've heard stories about fume hoods.
Yes, historically, many perchloric acid explosions were linked to fume hood ductwork. If spills or vapors weren't properly managed, the acid could condense in the ducts, react slowly over time with accumulated organic grime, oils, or wood dust in there, forming sensitive perchlorate residues.
Just waiting for a spark or maybe even just vibration to set them off.
Exactly, a hidden accumulating hazard. Modern perchloric acid hoods are designed specifically to prevent this with washdown systems and non-reactive materials, but the historical incidents are a stark warning.
Okay, now let's look at a compound that kind of blends oxidation with inherent instability. Peroxyacetic acid. The Handbook flags some really surprising triggers for this one.
Oh yes, peroxyacetic acid, C2H4O3. It's widely used as a sanitizer, a bleaching agent, but it's also an explosive liquid itself.
Yeah.
Its preparation needs really strict anhydrous, water-free conditions.
And Bretherick highlights a couple of major hazard pathways.
2 key ones. First, a known risk, reacting it with acetic anhydride. This can form acetyl peroxide, which is notoriously unstable and dangerously explosive. That's perhaps more predictable for chemists working in that area.
But the second one, this is the one that seems really insidious, especially in a lab setting. It involves adding simple chloride ions, like table salt.
You got it. We're talking sodium chloride, potassium chloride, just common, simple chloride salts. Adding these to aqueous solutions of peroxyacetic acid can trigger a violently exothermic decomposition.
Just adding salt can cause it to decompose violently.
Wow. The mechanism isn't fully detailed in the summary, but it suggests the chloride ion somehow initiates or catalyzes a rapid breakdown. This leads to a huge, fast release of heat, which causes chlorine gas to bubble off vigorously, the solution boils away, and often the remaining residue just deflagrates. Pops or flashes.
Wow.
It probably involves forming some highly unstable, transient, inorganic chlorine species, maybe chlorine oxides or something similar, that then just rip the peroxyacetic acid apart. Who would think adding a pinch of salt could lead to a chlorine-releasing decomposition, potentially violently? That's exactly the kind of non-obvious hidden hazard Bretherick is designed to capture.
Absolutely counterintuitive. Okay, let's shift gears now to compounds that are dangerous, not because of what they react with, but because of what they are. The endothermic compounds, the ticking time bombs.
Yes, these compounds have energy literally stored in their chemical bonds, making them intrinsically unstable. They don't necessarily need another reactant. They just need a trigger heat, shock, sometimes friction, to release that stored energy, often catastrophically.
And the classic example has to be acetylene, right? C2H2.
Absolutely. Acetylene is highly endothermic. It holds about 4.58 kilojoules per gram of energy just waiting to get out. This inherent instability means that pure acetylene gas is actually explosive above about 2 bar pressure.
Only 2 bar, that's barely above atmospheric pressure.
Right, which is why you can't just compress pure acetylene gas into a cylinder like you do nitrogen or oxygen. It has to be dissolved in a solvent, typically acetone, which is itself held within a porous, inert filler material inside the cylinder. That keeps the acetylene molecules separated and stabilized.
But the really big danger with acetylene, particularly in industrial settings or older labs, is its reaction with certain metals.
Yes, the formation of metal acetylides, especially with heavy metals. Copper, silver, mercury are the big ones.
And these acetylides are bad.
Very bad. They're often highly sensitive, crystalline solids. They can detonate with just friction, impact, or mild heat. The real insidious part here is often the time element. There are numerous documented cases of explosions happening during maintenance on, say, copper piping or copper condensers that were used in acetylene processes. Over months or years, trace amounts of acetylene react with the copper surface.
Slowly building up a layer of copper acetylide inside the equipment.
Exactly. A hard, brittle, highly explosive residue forms just sitting there.
Yeah.
Then, maybe years later, someone goes to do maintenance, they bang on the pipe, use a wrench, create some vibration, and boom, catastrophic detonation initiated by disturbing that old accumulated deposit.
So it's not a sudden failure, it's a hazard that grows quietly over time.
Precisely. A perfect example of a passive hazard becoming active without any immediate warning signs. It highlights the need for understanding the long-term compatibility of materials.
Okay, another endothermic nightmare fuel, diazomethane, CH2N2. Chemists use it, but it seems incredibly risky.
It is. Also highly endothermic, same energy content as acetylene actually, 4.58 kilodegrees. The big risk here is that the undiluted liquid or even concentrated solutions can explode, especially if there are impurities present or rough surfaces or even solid particles.
Including its own crystals, if it crystallizes out.
Yes, even freshly crystallized diazomethane can be sensitive. This leads to some very specific handling precautions listed in Bretherick's. Things like avoid using ground glass joints on your apparatus. Avoid glass-sleeved stirrers.
Why specifically ground glass? What's the issue there?
Ground glass surfaces, when you look closely, are rough. They have microscopic peaks and valleys. These rust spots can act as nucleation sites or create friction, tiny hotspots, when surfaces rub together.
Ah, so those microscopic rough points can provide just enough energy to initiate the decomposition.
That's the concern. If you have concentrated liquid or gas trapped in those joints, the friction or localized heating could be enough to trigger the explosion. That's why the standard advice is to always work with cold, dilute solutions of diazomethane, use fire-polished glassware, avoid strong light, basically minimize any potential energy input, thermal or physical.
Handle with extreme care.
I see.
Got it. Okay, let's pivot now to materials that might seem safer, like metals or common reagents, but hide dangers, maybe behind a protective layer or just through unexpected reactions.
A good example is lithium tetrahydroaluminate, Lyle H4, or LAH as it's often called, powerful reducing agent used all the time.
Right.
But Bretherick's records a specific violent explosion. It happened when someone was trying to decompose the excess LAH left over after a reaction. They added ethyl acetate, a common solvent often used for this quenching step, but they added it undiluted. Straight ethyl acetate onto the solid LAH residue.
And that was the mistake, adding it neat.
Yes. The reaction between LAH and ethyl acetate is strongly exothermic. Normally, you'd add the ethyl acetate very slowly, maybe diluted in an inert solvent like ether or THF to control the heat release. But dumping undiluted solvent onto the highly reactive solid
generated heat way too fast.
Way too fast. Instant thermal runaway. The solvent likely boiled violently, splashed, maybe built up pressure, leading to an explosion. It highlights the importance of controlling the rate of reaction, especially exothermic ones. Dilution and slow addition are key safety principles.
Okay, and then there's a metal that seems totally benign, but the handbook calls it out, aluminum. The silent killer. That sounds dramatic.
It does, but there's a reason. Normally, aluminum is incredibly safe, precisely because it instantly forms a tough, thin, inert layer of aluminum oxide on its surface when exposed to air. That oxide layer passivates it, protects it.
Right, that's why aluminum doesn't rust away like iron.
Exactly. But if you remove that protective oxide film, the bare aluminum metal underneath is actually highly reactive.
How would you remove it?
Mechanically, for instance. Bretherick notes explosive reactions between aluminum and certain polytrifluoroethylene greases, common lubricants, specifically when the aluminum surfaces are under load, under pressure, or friction.
Ah, so like in a moving part.
Yeah.
A valve, maybe. The friction scrapes off the oxide layer.
Precisely. The moving parts physically abrade the surface, exposing fresh, bare aluminum metal directly to the organic grease or oil.
And bare aluminum reacts explosively with those greases.
It can, yes. Especially under the heat and pressure generated by the friction itself. It can lead to ignition, localized pops, or even significant explosions. It turns a simple mechanical interaction into a chemical hazard. But the incident with chloromethane gas, that's even more illustrative of hidden dangers.
The 70-meter pathway. Tell us about that one.
This was a really subtle contamination scenario. Chloromethane gas, probably from a nearby process or storage, managed to diffuse about 70 meters along a supposedly inert nitrogen line. This nitrogen line fed into a pressure regulator that had aluminum components inside.
Okay, so the chloromethane wasn't supposed to be there.
Definitely not. And over time, this chloromethane gas slowly reacted with the aluminum surfaces inside the regulator. It didn't cause an immediate problem, no explosion then and there. Instead, it formed pyrophoric alkyluminum compounds.
Pyrophoric means?
They ignite spontaneously on contact with air. So these compounds just sat there, accumulating inside the regulator, far away from the original chloromethane source.
Like a hidden chemical trap being set.
Exactly. Weeks later, someone went to do routine maintenance. They started dismantling the regulator. As soon as those accumulated alkylaluminum compounds inside were exposed to the air, poof, ignition.
Wow, that really drives home the dwell time issue. The danger wasn't immediate. It built up silently over time and distance.
Precisely. The initial reaction was subtle, 70 meters away. The consequence, spontaneous fire, only happened weeks later during a completely separate activity. A classic example of how hazards can develop unseen.
Okay, let's keep exploring that theme of hidden dangers, maybe in common solvents this time. Dimethyl sulfoxide, DMSO. Everyone uses DMSO. It seems relatively safe.
It's a fantastic solvent, very versatile. But it absolutely has reactive hazards. Bretherick warns specifically about mixing it with things like acyl halides or nonmetal halides like phosphorus trichloride or thionyl chloride. These reactions can be violent, even explosive, especially if things aren't kept cool or properly diluted.
So mixing hazards, but what about DMSO on its own? Isn't there an issue with heating it?
Yes, absolutely.
Sure.
Its thermal instability is a major concern, maybe even underappreciated. DMSO starts to decompose exothermically, releasing heat just above its boiling point, around 190 degrees C.
And this decomposition isn't gentle.
Far from it. It proceeds via a radical mechanism, which means once it starts, it can accelerate very, very rapidly. Tests done in confined containers simulating what might happen in a closed vessel or pipework. Even with small amounts of DMSO showed it could generate enormous pressure.
How much pressure are we talking?
One test cited resulted in a maximum pressure of 60 bar.
60 bar? That's nearly 900 psi, just from heating a common solvent a bit above its boiling point.
In a confined space, yes. That radical decomposition kicks off, generates gas, generates heat, which accelerates the reaction further. It's another classic thermal runaway scenario. If the container isn't designed to handle that kind of pressure instantly, It will rupture violently.
That's a serious warning for anyone distilling or heating DMSO. Okay, another angle. Polymerization hazards. Allyl alcohol.
Right, allyl alcohol, C3H6O. There's an incident reported where they were trying to dehydrate it using concentrated sulfuric acid, aiming to make diallyl ether. Standard enough reaction on paper, but it resulted in a violent explosion.
Why? What went wrong?
The suspected mechanism is complex, involving a couple of competing dangerous processes happening at once. The sulfuric acid and the heat from the dehydration reaction likely initiated uncontrolled polymerization of the allyl alcohol.
Okay, runaway polymerization.
But also potentially peroxidation. Allyl compounds can form peroxides, introducing unstable oxygen-oxygen bonds. So you might have had both runaway polymerization and decomposition of unstable peroxides happening simultaneously, both fueled by the heat of the initial dehydration reaction. A perfect storm leading to explosion.
Wow. And then there's benzotriazole. This one seems significant because it involved a large quantity and the material was thought to be stable.
Yes, benzotriols, C6H5N3. A 1-ton batch detonated during distillation, reportedly at 220 degrees C. The crucial detail here is that it had been held successfully at 160 degrees C under vacuum for several hours before they increased the temperature.
So it seems stable at 160, but 220 was the tipping point. Why?
Look at the structure. Benzotriazoles has multiple nitrogen single and double bonds. N-N bonds are inherently high energy, making the molecule intrinsically thermodynamically unstable, even if it appears stable kinetically at lower temperatures.
Like acetylene or diazomethane, that stored energy is just waiting.
Exactly. While it might have been kinetically stable enough to survive 160 degrees C for a while, reaching 220 degrees C provided enough activation energy to kick off the decomposition reaction. And once that started in a 1-ton batch,
it couldn't be stopped.
Right. The self-heating would have become uncontrollable almost instantly, leading to the detonation of the bulk material. Even though, interestingly, they noted that heavy metal impurities, which are often catalysts for such detonations, were apparently absent in this case. It was purely the intrinsic instability of the molecule at that temperature.
A sobering reminder that stable can be relative. Okay, finally, in this section, we absolutely have to cover the most common insidious lab hazard, peroxides and ethers.
Ah, yes, the old classics. Diethyl ether, tetrahydrofuran, THF. Many ethers, especially cyclic ones or those with secondary hydrogens next to the oxygen, are prone to forming peroxides on exposure to air and light.
And these aren't just simple peroxides.
No, that's the key danger. They tend to form polymeric peroxides, long chains, with multiple unstable O linkages. Things like polyethylidene peroxide from diethyl ether. These polyperoxides are often non-volatile, oily, or even crystalline solids, and they can be incredibly sensitive to shock, friction, or heat.
Which leads to the critical handling advice everyone learns, or should learn.
Which is that the main danger isn't usually the bulk solvent itself, which might only contain trace peroxides. The danger comes during distillation or evaporation.
Because the volatile ether boils off.
But the non-volatile explosive polyperoxides stay behind, getting more and more concentrated in the distillation flask or evaporator. You end up with a small amount of highly concentrated, highly sensitive, explosive residue at the bottom.
And then trying to scrape it out, or just the heat from the heating mantle hitting that last bit. Boom.
Exactly. Explosions often happen right near the end of a distillation when the flask is almost dry. And here's the really chilling note from Bretherick's about testing for them. It explicitly warns that peroxide contamination is often seriously underestimated by standard test strips or methods. It even cites an incident where a distillation still exploded even after a peroxide test strip had given a negative result.
So the test strip said it was safe, but it wasn't? How?
Maybe the sample tested wasn't representative of the residue building up. Maybe the peroxides were polymeric and didn't react well with the strip chemistry. Whatever the reason, the message is clear. Test strips are not foolproof. Distilling ethers to dryness, especially if they're old, uninhibited, or of uncertain history, is just playing Russian roulette.
An absolutely critical safety point. Okay, let's shift focus slightly to compounds where their built-in structural instability is made even worse by contaminants. We're really thinking about energy and pressure.
Metal azides and nitrile compounds are prime examples here. Sodium azide, MAN3, is a good starting point. It's used in airbags, some lab syntheses, but the solid itself can be explosive, especially if it dries out completely or gets disturbed.
And it has that secondary hazard with acids.
Right. If sodium azide comes into contact with acid, even weak acids or just moisture and CO2 from the air over time, it generates hydrozoic acid, HN3. Hydrozoic acid itself is a volatile and extremely explosive gas or liquid.
And there's that classic plumbing hazard associated with azides too, isn't there?
Oh yes, the drain danger. If solutions containing sodium azide are poured down drains, especially older drains with lead pipes or lead solder joints,
It can react with the lead.
precisely.
Yeah.
Over time, it can form lead azide PbN32, which is a primary explosive. It's incredibly sensitive to shock and friction. So you could have this detonator material slowly accumulating in your drain trap, just waiting for a plumber snake, or even just a hard knock to set it off years later. Another chemical time bomb created by improper disposal.
Terrifying. Okay, shifting to nitro compounds, TNT trinitrotoluene seems like the definition of a stable high explosive. Used in shells, demolition, sure, that's pretty robust.
It is relatively stable, yes, compared to primary explosives. TNT has a decomposition temperature around 297 degrees C, but Bretherick's reveals a critical vulnerability: its sensitivity to contaminants.
How sensitive?
Remarkably so. That 297 degrees C explosion temperature can plummet by over 100 degrees Celsius down to about 192 degrees C if it's contaminated with just trace amounts of things like fresh red lead oxide or significantly strong bases like potassium hydroxide.
Potassium hydroxide, a common lab base, can make TNT that much more sensitive. Why?
It's about catalytic decomposition. The strong base likely interacts with the TNT molecule, maybe forming unstable anionic species or complexes, sometimes called Meisenheimer complexes, with nitroaromatics. These intermediates are much less stable, much easier to decompose.
So the base basically lowers the energy barrier needed to start the explosion.
Drastically lowers it, yes. It erodes the thermal safety margin completely. It shows how critical purity can be, even for materials we think of as relatively stable explosives. Trace impurities can be catastrophic catalysts.
And there's a quick, specific example involving lead, tetramethylide.
Yes, tetramethylide, C4H12SN, an old anti-knock additive for gasoline. The handbook notes it forms explosive products simply on contact with a specific phosphorus compound, tetrachlorotrifluoromethylphosphorin.
Doesn't exactly roll off the tongue.
No. And that's the point. It highlights these non-obvious, highly specific reaction pairs between, say, heavy metal organometallics and complex halogenated compounds that you'd likely never predict without a resource like Bretherick's documenting the known incident.
Right, catching those obscure but deadly combinations. Okay, let's bring polymerization back into focus one last time, thinking about the sheer force it can generate. Acrylonitrile.
Acrylonitrile, C3H3N, the monomer used to make acrylic fibers and plastics. It is notoriously prone to undergoing rapid, runaway polymerization.
Which is why it's usually shipped with an inhibitor added.
Exactly. Usually something alkaline like aqueous ammonia is added to prevent spontaneous polymerization during storage and transport. Because if it does start to polymerize uncontrolled, especially under alkaline conditions, high temperatures, or if contaminated with metals, it goes wild.
And what happens physically when it runs away in, say, a storage tank?
The polymerization reaction itself is highly exothermic, releasing a lot of heat. But crucially, you also get a rapid phase change. The liquid monomer converts very quickly into a dense, solid polymer. This expansion in volume, combined with the immense heat generation,
Just blows the tank apart.
it generates pressure incredibly rapidly, often far exceeding what the tank can withstand. Violent rupture is a common outcome.
And that terrible incident with epichlorohydrin and sodium chloride, that seems like a perfect storm of reactive chemistry and human error.
It really was. A tanker truck, supposedly containing an aqueous solution of sodium chloride, was mistakenly unloaded into a storage tank that already contained epichlorohydrin.
A simple mixing error.
An administrative error that led to a mixing catastrophe. A very violent explosion occurred shortly after the transfer began. Powerful enough, reportedly, to knock down the wall of a nearby building.
Wow. And the investigation pointed towards mislabeling.
Yes. The editor of Bretherick's, analyzing the incident, strongly suspected that the tanker didn't actually contain sodium chloride, NClO2, but rather sodium hypochlorite, NClO, common bleach solution. The name sounds similar, easy to confuse on paperwork perhaps.
And hypochlorite reacts badly with epichlorohydrin.
Very badly. Hypochlorite would be expected to react rapidly with epichlorohydrin to form highly unstable, energetic alkyl hypochlorite compounds. These are known to be shock-sensitive and prone to explosive decomposition. So a simple labeling mistake likely led to the inadvertent creation of a large batch of unstable explosive intermediates. A stark reminder of how critical accurate labeling and material handling protocols are.
Absolutely. We've covered so much ground here, from the basic physics of energy release to these incredibly specific, sometimes obscure chemical time bombs.
Yeah, it's a lot.
Yeah.
But if you try to synthesize it, the big lesson seems to be that these reactive hazards, really boil down to uncontrolled energy release. Whether that energy was stored inside the molecule, like in endothermic compounds, or generated by a reaction running too fast, like exothermic runaways, maybe kicked off by a catalyst or contaminant.
And what really strikes me going through these examples from the handbook is how often the danger involves seemingly ordinary things. Common solvents like DMSO or ether, familiar metals like aluminum.
Right, they become lethal killers, not necessarily on their own, but because of subtle factors. Tiny impurities, losing a protective oxide layer, an inhibitor getting used up over time.
Simple actions we do all the time, drying a precipitate, opening an old container, distilling a solvent down. These can be the trigger points for catastrophe if we're not aware of the hidden potential.
Exactly. Which brings us to a final thought, something that weaves through many of the worst incidents we've talked about. The dimension of time. Specifically, the induction period.
The delay before things go bad.
Yes. Think about the ethylene oxide cylinder exploding 8 hours after contamination, or the slow buildup of copper acetylides over years, or that aluminum regulator where the hazard formed 70 liters away and only ignited weeks later.
In all those cases, there was a period where things seemed fine. Maybe the reaction was proceeding subtly, silently, before the violent phase kicked in.
Precisely. That initial quiet period can lull people into a false sense of security. They might think the process is stable, under control, maybe even leave it unattended, only for the runaway to start hours or days later.
So that leads to a final, really critical question for anyone working with or storing chemicals, doesn't it?
It does, and it's this. Knowing that so many of these devastating hazards don't start with a bang, but with a whisper, knowing they often have this subtle build-up phase, this dwell time, before they accelerate violently. How do you account for that potential? How do you factor in that quiet energy accumulation or hidden reaction happening in your own procedures, your storage protocols, your maintenance planning?
Recognizing that something might still be cooking silently, building pressure, or forming an explosive residue even when you're not looking, and that seems like maybe the most crucial proactive step you can take.
It could well be. Thinking about that hidden timeline might be the key to preventing the next unfortunate incident.